Coming back to our main storyline, we're still in part 2 called Optimization with Model Space Multiscale. We've learned about the FWIME optimization scheme, we've shown you how our model space multiscale approach is necessary for the success of FWIME, and now we're going to revisit the numerical examples where we previously failed, and we will show you that we can now recover accurate solutions. Okay, let's go back to our numerical examples. If you remember, we succeeded at inverting purely transmitted waves from the borehole experiment. Then we tackled the inversion of purely reflected waves. We examined what we called a pathological case on a V of Z model, and we showed that even if the tomographic component of the FWIME gradient seemed promising, its amplitude was too weak compared to the Born component. And we're now going to see that our spline parameterization is going to fix that. Back to our V of Z pathological case. I really like this example because it perfectly illustrates the power of FWIME and the necessity of pairing it with our model space multiscale approach. I recall the experiment. The top left figure shows the true model that includes a sharp horizontal interface located at a depth of 2.1 km. The bottom left panel is the initial model, and the right plot shows the two vertical velocity profiles. We computed the Born component of the first FWIME search direction, which did not seem to be very useful at guiding the inversion towards the global solution. Then we computed the tomographic component, which did seem promising, but its amplitude was too weak. And this was confirmed by computing the total FWIME search direction. Now we incorporate our spline parameterization, and for the initial grid, we use a regular sampling that is 5 times coarser on both Z and X directions. We map each search direction component onto the spline grid and then back to the finite difference grid by first applying S adjoint and then S. We can now clearly see the benefit of such parameterization. Each panel on the bottom row is displayed with the same color scale, and we see that the amplitude of the Born search direction is now overwhelmed by the tomographic one, which shows that we were able to extract the useful low wave number update from the first FWIME search direction by simply applying a linear spline mapping, and we are now in a much better shape. And here we compare the initial search direction before the spline mapping with the ideal search direction, which is the difference between the true and the initial models. And our new initial search direction seems more promising. We now revisit the example based on the model proposed by Mora in 1985. Recall the true model and the initial model. In the first section of part 2, we computed the Born, tomographic, and total search directions for this numerical example. Here, for our initial spline grid, we're going to use a regularly sampled grid where the sampling in X and Z is 5 times larger than the finite difference one. After mapping each component on the spline grid and back to the finite difference grid, we can see that again the tomographic component dominates, and the first FWIME search direction seems very promising. Let me now show you a sequence of 3 FWIME inverted models, and each panel will correspond to the inversion on a given spline grid. This is for spline 1, this is for spline 2, and this is the FWIME inverted model on the last spline grid, which coincides with the finite difference grid. The result is very accurate, and the shadow zone located between the bottom of the anomaly and the horizontal interface is well recovered. Initially, the Born component was inserting sharp interfaces that were mispositioned because of the missing low wave number in the initial model. We saw that now, with our model space multiscale approach, we delayed the inclusion of such high wave number features until the larger scale features were correctly captured. I want to remind you that throughout this inversion process, the only parameter we adjusted was the spline grid refinement rate. We used regularly sampled spline grids, and each refinement was performed by dividing the sampling in each direction by a factor of 2. Each grid refinement was triggered when the stepper could not find an optimal step length. And indeed, we kept the same epsilon value. So even though this is a toy problem, our results really show you how we are building an automatized solution that needs very little tweaking. We can further improve the result by using the FWIME inverted model as initial guess for a conventional FWI. And as we explained in the theory and design part, this is mathematically equivalent to adjusting our trade-off parameter epsilon to very high values, and the result is displayed on this figure. This is a recap of the various results obtained for this numerical example. As expected, FWI converged to a non-useful solution as shown on the top left panel. In the top right panel, we see that FWME without multiscale also gets trapped in a local minimum. However, by combining FWME and the multiscale approach, we dramatically improved our previous results, as the bottom left figure indicates. We saw that we can accurately invert reflections, and now we test if our method can invert a dataset composed of only diving waves. For this test, we built a laterally invariant model whose velocity values are linearly increasing with depth, starting at a depth of 0.5 kilometers. This model is 16.5 km wide and 2.8 km deep. We begin with a constant initial model shown in the bottom left figure on the screen, and the velocity profiles are plotted on the right panel. We simulate a surface acquisition geometry where receivers are placed at every grid point. The source we use contains energy strictly limited to the 3 to 12 Hz range, and the maximum recorded offset is 16.5 kilometers, and indeed the dataset is dominated by diving waves. So we guide you through the first step of FWME, and if you've watched our previous videos, you're probably starting to know the drill. So we compute the initial data difference shown in the panel in the middle of the screen. And this data difference is dominated by the diving waves from the observed data that our initial model cannot generate. And the next step is the computation of our initial p-tilde-opt via the variable projection. And note here that we decided to use time lags for the extension of p-tilde-opt. And we extract the time lag common image gather from our p-tilde-opt at x equals 9 km. Not surprisingly, we can see that the diving wave event has been mapped into p-tilde-opt away from the physical axis, shown in green on the right panel. And as we go deeper into the section, the kinematic error accumulates and the event is mapped further and further away from the physical axis, as indicated by the pink arrows. Another interesting observation is that for shallow depth, the kinematic error is not too large, and this diving wave event is contained within a region close to the physical axis, displayed in the pink rectangle on the right panel. Intuitively, this is the region where we would not need to use any extension for p-tilde-opt. And this is also where the linear approximation made by conventional FWI would still be valid. You will see that in fact, conventional FWI is able to retrieve an accurate solution only within this region of the model, that is, for depth smaller than approximately 1.6 km. We applied a data space multiscale FWI workflow with 4 frequency bands. This figure shows the final inverted model. As we mentioned, FWI is able to only recover an accurate solution down to approximately 1.6 km. Note that for FWI, we tried to apply our model space multiscale workflow by parametrizing the velocity model on a sequence of spline grids. We also tried to use illumination compensation, however we were unable to improve this result here. Now we compute our first FWME search directions on the finite difference grid, and all panels are displayed on the same color scale. And notice that the amplitude of the Born component is already overwhelmed by the tomographic one, before we even apply our spline parameterization. The total FWME search direction shown on the bottom left panel seems very promising. And here this search direction was computed with the exact same mechanism as we used for the borehole and the MORA datasets. Indeed, after mapping onto the spline grid, we obtain a smoother and even more promising initial search direction. Now we're going to show you a sequence of 3 FWME inverted models. Each panel will correspond to the inversion on a given spline grid. And for this inversion, we also applied an illumination compensation to boost the deeper parts of the FWME model updates. And this is the inverted model after spline grid 1. This is the inverted model after spline grid number 2. And this is the inverted model after spline grid 3, which coincides with the finite difference grid. We can also further improve our result by using the FWME inverted model as an initial guess for conventional FWI, which suffers from less edge effect. And here for FWI, we inverted the full data bandwidth simultaneously. And let me flip back and forth a few times between this panel and the true model to compare the quality of our result. FWME was able to recover an excellent solution. And again here we applied the exact same code as the one for both the borehole and the reflection datasets with a constant trade-off parameter value. As we explained in part 1 theory and design, we do not adjust or modify our annihilating DSO operator term with the type of waves we are inverting. And here we summarize the different inverted models displayed with the same color scale. This shows the velocity profiles of the true and initial models extracted at x equals 9 kilometers. The pink curve shows the conventional FWI inverted model, and here the red curve shows the profile extracted from the inverted model computed by FWME and followed by FWI. It shows an excellent match with the true solution. To summarize, we revisited the numerical examples that gave us trouble in the first section of this presentation. We applied our FWME and model space multiscale workflow, and we saw from these numerical examples that our proposed method is able to invert each type of waves when the initial model and the available frequency content are such that FWI converges to a local minimum. We successfully inverted transmitted waves simulated from our borehole setting, reflection data generated with a similar model as the one proposed by Mora in 1985, and finally diving waves. Again, the key message here we want to convey is that we're building an automatic process. We saw that each wave type was inverted with the same methodology, and we did not need to modify our annihilating term in our objective function. From these examples, it seems that our modified DSO operator is able to guide our inversion to the global minimum regardless of the wave type. And finally, during the inversion process, no parameter needs to be adjusted. In the next part, we test our method on benchmark numerical tests by simultaneously inverting all wave types. Okay, so now we're done with part 2, entitled Optimization with Model Space Multiscale. In the next release, we're going to test our method and show you some excellent and exciting results on 3 benchmark tests. We really hope you enjoyed this presentation. And finally, if you have any questions or comments, please do not hesitate to contact us. We will look forward to talking to you further.